permutation groups. If you consider a set, we can take a simple one with 3 elements. So consider the set, say S, with 3 elements, 1, 2, and 3. Then we can say that there are 3 factorial. There are 3 factorial, which is 3 times 2 times 1, which is 6. 3 factorial ways, 3 factorial ways of representing, the ways of arranging, you can say, of arranging the elements in the set. So we can arrange them in this form. We can either write them as just 1, 2, 3. That's one arrangement. We can arrange them instead of 1, 2, 3. I can have it as 1, 3, 2. I can start with 2, 2, 1, 3. That's another arrangement. I can start with, I can have 2, 3, 1. I can start with the number 3, so I can have 3, 1, 2. I can also have it as 3, 2, 1. Are those 6? 1, 2, 3, 4, 5, 6. So I don't think there's any other way. We have not, because we have starting with 1. We fixed 1 and had 2 and 3. Then we fixed 1 and interchanged 3 and 2. So we have 1, 3, 2. We now start with 2 and write 1 and 3. Then we have 2 and have 3 and 1. Then we fix 3 at the first slot. Then we have the other 2 places occupied by 1 and 2, and they are interchanged 2 and 1. So these are the 6 ways we can arrange the elements of this set S. So each of these arrangements is a permutation of 1, 2, 3. So we can say that each of the arrangements is a permutation. It is a permutation of 1, 2, and 3. Those are the elements of the set S. Now, with these permutations, we can write the permutations in form of some notation. For convenience, instead of having to list them this way, we have a better way of representing these permutations. So, and that is why in mathematics notations are very common, because they shorten our work and make it more presentable mathematically. So we can write each permutation in form of a function. We can write each permutation we can write each permutation in form of a function in two rows as follows. So the three now are cleared, but since you already have them, so we can say that maybe the first one, we can represent the first one as F1, and F1, we write it as this. The first row, we have 1, 2, and 3. That is the set S itself. And then in the second row, we have the rearranged form. That is the permutation, which is again 1, 2, 3. F2 as 1, 2, 3. And then when you, the second row, we have the rearrangement, which was 1, 3, 2. 1, 3, 2. F3 as 1, 2, 3, the first row. And the second row, we have now that permutation, which is 2, 1, 3. 2, 1, 3. F4 as 1, 2, 3. And the second row as the rearranged form, which is 2, 3, 1. 2, 3, 1. F5 as 1, 2, 3. And the second row, the rearrangement there is 3, 1, 2. And F6 is 1, 2, 3. And the second row is the permutation, which is 3, 2, 1. 3, 2, 1. So all the 6 permutations can be represented in this form. And the first row, when you use now this representation of a permutation, usually the first row represents the elements of the set, or is just the whole set. And the second row corresponds to the images. So that now for F1, 1 is mapped to 1, 2 is mapped to 2, 3 is mapped to 3. For F2, 1 is mapped to 1, 2 is mapped to 3, 3 is mapped to 2, and so on. So the second row there represents the images. So we can say that in this representation, the first row, let me just continue it here. Let me use a different color. The first row of the permutations represents the elements of the set. And the second row represents their images. Represents their images. So in other words, we can say that, let me put it in notation form up there. In other words, we are saying that when you represent a permutation in this form, in two-row form, the first row are the elements, the first row are the elements of the set. And the second row are the elements in rearranged form or in the images. And then you put that in brackets. So it is now understood that when you represent a permutation in this form, in this two-row notation, then it means that the first row just captures all the members of the set arranged in their correct order, and the second row is the images where this function maps each of the point or each of the elements of the set is represented in the second row of that notation. So that now at this point, we can define a permutation. We can now officially define a permutation, having had the discussion of the concept. So definition. Let S be a finite set. Let S be a finite set of n distinct elements. Then a one-to-one function, say f from the set S to the same set S, is called a permutation. It's called a permutation of degree n, denoted by f is equal to, so we have, S has, the first row would represent all the n elements or all the n members of the set. So we can say we have A1, A2, A3, all the way up to AN. And then the second row will represent, will still have the same n elements, but now they may be rearranged. There could be some rearrangements so that the elements in the second row will be B1, B2, B3, all the way up to Bn, where f of A1 is equal to B1, f of A2 is B2, f of A3 is, and so on. So we can say that this, where, let me continue up there, where f of AI is equal to BI for I 1, 2, 3 up to n. So That's the official definition, but we have discussed the whole concept of permutation. Then now we can say that since S has n elements, and we say that the number of rearrangements of n elements is n factorial. For 3 elements was 3 factorial. Now, since S has n elements, the number of such permutations will be n factorial. So we can say that since, clear this, since S has n elements, then we can say that there are n factorial, permutations of S. There are n factorial permutations of S. And also we can say that now when we put together all those permutations of a given set, then we denote that collection of all the permutations of a given set. We use the as annotation. So the set of all permutations is denoted by S subscript n. S subscript n there is the set of all permutations of the set S of n elements, where S has n elements, and is called the symmetric set. It is called the symmetric set. So, for example, when our set had 3 elements, when S is equal to 1, 2, 3, Sn or S3 is the set of all the permutations, all the 6 permutations which we found, and we called them F1, F2, F3, F4, F5, F6. So each of these was a permutation, so we represented each of them. So the entire S3 is a set of all the permutations of the set S with 3 elements, all the arrangements of 3 elements. And then, now that we have a permutation from one set to the same set, and we have defined the permutation as a function, then it is possible to have a composite function, or to have a composition of such functions, where the function itself is a permutation, and we can have a composition whereby the permutation is carried out more than once. One permutation, and then the result is subjected to another permutation, and the result is subjected to another permutation, and so on. So that now means that we can look at a case of a composite map where the map is a permutation. So we can have a series of permutations performed to give us an outcome, which is now the result or the image of a composition of those permutations. So let's say something about the composite permutations. Now, when you perform more than one permutation in a sequence, then you have a composition you have composite permutation. So we can say the composite or composition. Let's have it as composition of permutations. Composition of permutations. Just like we can have a composition of any other mappings. So composition of permutations. So we have defined the symmetric set as a set of all permutations of members of a set. So we can say that the symmetric set say Sn, together with a composition of function together with a composite function denoted by Sn under the composite map is a non-commutative. It is a non-commutative group. So you can see now here what we have. Our Sn is a set, which is now the symmetric set, and we have defined the symmetric set as a set of permutations of a set n of a set S with n elements. Then now the dot here, the composite map here, is a composition or a composite function for two permutations, or for permutations in Sn. Then now we are saying that this system now, this algebraic system is indeed a non-commutative group, meaning that it will satisfy all the group properties except from the fifth one, which is the commutative property. So we would like to illustrate this, because for non-commutativity, all you will need to show is that Sn under this composite map is not commutative. It is not commutative. So we can let F and G, let F and G be two permutations. Let F and G be two permutations defined on Sn. And then we can say that then by definition, F and G, by definition, F and G are one-to-one and onto maps. So we can say F and G, by definition of permutations, we can say that F and G are one-to-one and onto maps. And consequently, the composite mapping, that is now G composite F and also F composite G are defined by, so we will define, even under permutations, we will define the composite map in a similar manner that we defined under other types of mappings. So F composite G of X will be defined by F of G of X, that way, for every X in the set S. And if we reverse the order now, G composite F of X will be G of F of X for every X in the set S. So you will let this composite map act on every element of S, giving you an image for each, and you can now obtain the resulting permutation as a result of the composite map. So we can illustrate this with an example where we let our F and G be specific permutations, and then remember we claimed that the Sn under the composite map, or the symmetric set together with the composite map, is not commutative. So we would like to show that that property of non-commutativity is satisfied or can be illustrated using some permutations of a set. Let's say, for example, can have an example there. Example, if we let F be this permutation. We have elements A, B, C, D, C. In the second row, we have C, A, D, and B. And the other one is G. G is the permutation still on the same set A. Sorry, there are no commas in, as you write the permutation, you don't put commas. So A, B, C, D. And the second row is B, C, D, A. So we will interpret this as the permutations in two-row notation, where the first row is the set, the second row is the image under that permutation. So we want to, what this means is that F maps A to C, B to A, C to D, and D to B. Then G maps A to B, B to C, C to D, D to A. Then we can now see what happens to the composite map. So to obtain the composition of this, if we want now G, the composition of G and F, so G composite F, we will perform it on each element of the set. So GF of A, by definition, is G of F of A. That's how we have defined. But now f of A is the image where f maps A in the permutation f. So f of A is C. So this becomes G of C. G maps C to D. So the result here is D. Then in a similar way, we take the other composite map, G composite F of, say, the element B, which by definition is G of F of B. Hope we are together, because the next one I will ask you to work out. So F of B, F maps B to A. So F of B is A, meaning that we have G of A. And G of A is B. So the result there is B. G composite F of C. G composite F of C is G of F of C, which is from F, F maps C to D. So this becomes G of D. And G maps D to A. So the result here is A. And finally, G composite F of D by definition will be G of F of D. So F of D, F maps D to B. So F of D is B. Therefore, G of B. G maps B to C. So the answer here is C. And now, this way, you can write the composite permutation G of F, GF. So I can now write the composite map. I can have it up here. We already have the permutations. So we can say here, therefore, this composite map, G of F, is this permutation. A, B, C, D. Then A is mapped to D, so the second row will be D. B is mapped to B. C is mapped to A. D is mapped to C. So that is the composite map.